All right, let's go ahead and get started. Welcome to our the first outside colloquium of the fall 2022 semester. So I'm very happy to welcome Dr. Merab Gogberashvili back to Fresno State. So Merab and I have a long history going back, I think, to 2003 when he first came and visited. And he's responsible for like a lot of my first papers that were highly cited. And so he was kind enough to include me on some work that he was involved in at the time that was called brain world scenario. So I don't know if you're studied theoretical physics, the brain world scenario was a huge deal like in early 2000 and so forth. He's one of the originators right here. So Merab has had very broad research interests, so not only brain world stuff, but now he's interested in mirror world particles and LIGO signals and various other things. And so he's from Tblisi State University, and today he's going to talk about LIGO signals from the mirror world. Let's welcome Dr. Gogberashvili.
Okay, it's my pleasure to be here. I thought 12 years. 12 years ago I have last collective here, and the brain was here. Now it was popular. Now nobody works on this. Another goal, it's gravitational waves, very deep about this. Let me talk about this.
Can you speak louder than I hear here?
Oh, so can you speak a little bit louder?
Something wrong with this. Okay. It is one of my talk. Do you hear me now?
No.
No?
Scoot down closer, guys. Just scoot down closer.
More louder? Or it's okay? Okay. So it is 4 parts, different colors. I will speak about parity, violation, mirror particles, which probably exist. About history and detection of gravitational waves, small part. And then I will be red part analysis of LIGO signals, which is some unpredictable and unexpected. And last part is the original part, our suggestions, how we can improve the understanding of the observer. Okay, start with parity violation in particle physics. It is 50s that problem so-called tau theta puzzle. It was 2 particles. They thinking it was 2 particles. They have decay of 2 pions and 3 pions. And it appears that it's just 1 particle, Camazon we call it nowadays Camazon, which violates parity. What is parity or mirror symmetry? We have a coordinate system, yes, so numbers. If you look in the mirror, you reflect one of them, you can reflect 3 of them or just 1 of them. And usually we expect that in mirror we see similar physics, just another guy with left hand is right handed, my heart is another side, but otherwise it's okay. So everybody believes that same should be in particle physics. Because it's gravity respects this mirror symmetry or parity. Electromagnetic will also respect, but it was not clear about weak interaction. And Lee and Young suggest that maybe parity violates weak interaction. They suggest experiment. It is famous new experiment about weak decay of cobalt to nickel. Okay. So it's not low.
Yeah.
Pincho's expert. She uses this all the time, yeah.
Try now.
It is better?
Go on, yeah. Is it on? Is everything on?
Yeah, it's on.
Right.
It's on? No, this isn't on.
We'll say you gotta get everything on.
Oh, somebody didn't turn off the battery.
Hold on.
No battery.
Oh,
Here.
one, there's another one.
Okay.
Yeah, this one to wear more or less.
You guys, we didn't have Roger here today. Well, don't do anything. I'll put some on your head and you go for it. Here you go.
It is better?
Yeah.
All right.
Good job.
Oh. Mirror will disappear. Because we're browsing what happened.
Superposition.
Okay.
Right.
So you know that we have two kinds of vectors. Already studying on the first grades. We call polar vectors and pseudo vectors. Yes, polar vectors is like ordinal radial vector, and then you can by this obtain velocity, acceleration, force, momentum. All these are polar vectors because radial vector is polar. And in mirror, we know how it reflects. If you go direction of the mirror, somebody coming to you, so it is reflected. But we have another type of vectors called pseudo vectors. It's connecting with rotations. We have some surface and left or right-handed rule, and normal to the surface. We describe vector, which is not a normal vector. It's just oriented surface, but we call it pseudo vector. And this guy is not reflected in the surface. For example, if you have rotation and say that I have right hand rule, that if you rotate this way, vector should look in the direction of front. In mirror, you see the same rotation, so it's also pointing same direction. Yes. So example of such vector is the spin, for example, magnetic field. And then we can check parity relation by this vector. In magnetic field, we look what happened particle with spin. And we have quantum number we call chirality, which is when you have normal vector like velocity or momentum and its spin. And if direction of two spin and momentum coincide, we call this right particle. If it's opposite, we call left. And if a particle have mass, this is not a good quantum number because I can go faster in another coordinate system. It change velocity, it become from the left to the right. But if particle is massless, like neutrino, it is good quantum number. And then you can change if it should exit left neutrino and right neutrino. It seems that okay, it should be any left or right particle for us. It's important matter or antimatter, a solution of Dirac equation. But somehow it appears that nature don't care about matter and antimatter, but very important is left or right. So now everybody, Dirac himself write his equation in Dirac representation, so-called, when we have spinor with particle antiparticle. At standard model, now particle physics is written in Weyl representation when you have left and right. Because standard model is a left model. All particles or spinors are there left. So its spin should be opposite to momentum. And why it exists, we don't know. But it's starting from this experiment. Wait. Pointer. Okay, it is cobalt and weak decay. Here is magnetic field direction. And we see it is electron and antineutrino. We don't see neutrino, but can detect electron and its direction. And it depends of direction of magnetic field is asymmetry. So it shows that there we violate mirror symmetry. We have not this. We have preferred direction of fly of electrons. So it's another way. And so it was a direct measurement of parity violation or mirror symmetry breaking in weak interaction. It was shock for the time, and it appears that God is weakly left-handed. So it's strange, but what can be reason? We know that our space is isotropic, there is not left or right, so something wrong with our definition of particles. How we define particles? It is some guys, we don't see them, they have no space, no time, no special position. We have some strange equation like Schrodinger and right wave function, which depend on our normal coordinates, the classical. So possible that the reflection for particles we don't define correctly, and it's our mistake. So first idea was that we lose something. So when you have ordinary particles, and in a mirror also ordinary particles, so we see that weak interactions, they don't coincide. And Li Yang, which obtained for this Nobel Prize in '57, they suggest that probably we need here not ordinary particles, but some other particles, so-called mirror particles, which behave oppositely. It's, if you have left particles, they are right, and then you have your coordinates are okay, and it's just everything is symmetry. But for this we need to introduce some doubling of our particle states, or introduce right particles or mirror particles. So then it was Landau's idea that so maybe parity is ill-defined, and we need to define CP symmetry. And real right particles should be CP reflecting particles. And then, okay, right particle should be P is violated, but CP is not violated, because Dirac equation is symmetric, so it respects CP symmetry. So Dirac, anti-Dirac, and CP symmetry is okay. But then another shock that CP symmetry also violated by weak interaction. Example is, for example, this omega plus and its neutrino and positron. If we have C conjugation, we should have this kind of process, but it not exists. We don't observe this. We have this observe, it is CP. But again, we have not this fact. So somehow we have CPT symmetry violation, and so now again we have problem of left-right asymmetry, which seems very unnatural, because our space seems that they respect some kind of rotation. We have neutrinos which rotate one direction, spin is not rotation, but kind of rotation, and not other way. So to explain this CP, it's also famous picture of Marcus Escher. We have two quantum numbers, C and P. One is left and right, and white and black. So we can say that charge is color, and direction is P. And CP, we have this picture, but you can notice that we have not exactly match. So anti-volt disappeared. So our world is a little bit asymmetric in CP. So only in K meson, D meson, so some kind of weak interaction, we have CP violation. But there's a more general, there's CPT theorem, and we believe that CPT is okay, good, should be good. Otherwise, all our standard model will break down. Okay, now after this, new models appeared. It starts by Russians. It's Gogberashvili, it is 60s. They say that in mirror we don't see ordinary particles. It is mirror particles. So we have ordinary particles like standard model particles, and mirror particles. And this symmetry respected in mirror because, okay, this reflection or mirror means this. Then it is a left-right symmetry. Restore it with, but we have these two bunch of particles which are behave differently under parity, under parity. And at first they decide that they should be exactly symmetric, or everything should be symmetric, and calculate that they cannot interact by ordinary way. For example, photon. We know photon, every particle has antiparticles, yes? Photon's antiparticle is photon itself. But what is mirror photon? And can electron absorb or interact with mirror photon? So it seems that it's impossible. So as I thought, nature somehow prefers left and right, not particle antiparticles. We can measure antiparticles, but we cannot observe mirror particles in this model. So these two walls, our and mirror, cannot interact with ordinary standard model bosons. They should be exactly divided. Only way, just for gravity maybe, or for neutral particles mixing. So then some cosmology started in 90s, 80s. You know these cups, everybody can see the standard model for short. We have ordinary world, ordinary particles, and then we have mirror standard model. Should be mirror particles, which is not is the same as in our world. So it's like brain world model. I told about this 12 years ago, but not in other brain, but in our world. So probably here we have now mirror particles, but we don't see them. So name of mirror matter is different papers, is shadow matter or Alice matter. Alice because Alice Wonderland, famous book. Yeah. So maybe you read some Alice strings or something, you don't understand what it means. Just it is Alice from the book.
So, Rob, do you think these mirror particles live in your brain? Is that what you're saying?
No, here,
They're
in
here.
our world.
They're here, okay.
We don't need to introduce anything. Just restore symmetry of standard model. So it is ideal.
Are you saying that they exist coinciding in the same space or similar space next to each other?
Yes, so I will talk about this, show their properties, their cosmology, so and then we'll come with the big observation properties.
Okay.
Okay, so probably we have some mirror world in somewhere here, shadow world. So if our world is standard model, so our standard model prime is right, so we restore the symmetry. So our standard model group should be just product of ordinary standard model left and prime right, with their own photons, their own gamma bosons, omega bosons and gluons and particles. Everything is double. And it is general Lagrangian of this. And I want to remind that first grand unification group, which was introduced in the 70s, is anticipate even SU5 famous model. It was introduced by Patti and Sala. It was idea just restore this symmetry, left-right symmetry. Because it's very unnatural to have this asymmetry, and first idea of grand unification was somehow restore the symmetry. Now motivation. Of course, at first, elegance. Because I don't understand why I should have only left hand and not right. It is good. Why don't have other hand? Now, historical analogies. If we have Lorentz invariance for spinors, then we discover antiparticles. But if we want to have exact parity symmetry, then probably we need mirror particles. Now, what they can explain, and a lot of papers doing what this is. So, in cosmology, of course, if I have some matter here, I don't see them, first idea is the dark matter. I can interact with them only by gravity, is very similar to dark matter. Then high energy cosmic events, we have very strange signals, X-rays, gamma rays, and others we cannot explain. And possibly, of course, if some particles are, they can explain this. Now in astrophysics, it is machos, it is not Spanish word, it is massive, compact, hollow objects. Okay, physicists like these names. So it is some, with micro lensing we see something in galaxy, but we don't understand what it is. It is not black holes, it is maybe black dwarf stars or something, but possibly we call general word is machos. Possible, of course, it is mirror stars, which we don't see. Also isolated planets, dragging force on Pioneer, also different, it is different problem. Missing comets in, we have some gravitational fluctuation, we don't understand what it is, so it is mirror comets. And mirror bodies who bombarding on the Earth, and several events they want to explain by mirror matter. Example is Tunguska meteorite, you know, it was 1908 in Siberia, something will blow up and nothing, no remnants. So it was, if it was mirror comets, then of course we don't see this mirror. Somewhere it exists, but we cannot interact, we cannot find. So about this, a lot of papers you can see. Okay, I don't mention this. So in particle physics, if you are particle physics experiments, where I can see this. This neutral mixing, yes, it is charge or bosons I cannot observe, but neutral particles can mix. This second Higgs, I have two Higgs, one is a standard, another mirror, so they are mixing. Stereo neutrino, because we have left neutrino, the right neutrino, we have problem with mass because ordinary neutrino is only left-handed, we need the right-handed neutrino to write coupling. And if mirror neutrino right-handed exists, we have write small coupling and explain mass of neutrino. Then is photon mixing also, photon, ordinary and mirror photon, and there is the anomaly in orthopositronium, and there is only 5 sigma anomaly, nobody knows what it is, and the people want to explain this with this coupling. And now experiments with anomalous disappearance of neutrons. Each ongoing experiments, and it's strange because it's also signal is more than 5 sigma. Somewhere neutrons disappear. I have entrapped neutrons, and after some time they disappear. So if they mix with mirror neutrons, it's okay, but it is one of the leading model to explain the experiments. So neutron disappear. So you see many experiments you not mention, not here, but people working on this.
Are you saying these particles have inertia? They have mass?
Yes, they have mass, they gravitate.
mass.
Yes, they have charges, but
Okay.
it's mirrored. It's different. So, yeah.
Okay, so the anomalous disappearance of neutrons experiment, so who did, where is that done?
There's several groups. One is in Grenoble experiment in France, and one is in Canada, underground experiment. So they agree with each other that there's something wrong.
Are you suggesting that
Maybe
very
it's okay,
okay.
yeah.
Of course, you call it anomalous.
So very big effect. So nobody knows what it is.
Are you suggesting that mirror neutron interaction is
Yes,
the
yes.
lack of source of neutrons that we
Neutron
develop
disappearance,
experiments?
yes. Because of mixing. We write coupling, we cannot exchange bosons, but we can mix. Like neutrino mixing, what we have left and right neutrino, similarly. Okay, so now some general properties of mirror particles, if they exist. So they have the same masses as standard model particles, same quantum numbers. interact with standard models only under, so they are singlet under ordinary standard model, and could be dominate for large distances. I mentioned dark matter, and can interact with us by gravity and by mixing, as I told now. So problems, if you have this model, that we have equal number, if you have exactly everything is symmetric, equal number of mirror and ordinary values. Then if you calculate BBN, Big Bang nucleosynthesis, yes. Then you obtain wrong number because all particle spices are twice of amount, and then you have more than 28% of helium, which is not observed. So to solve this, you should say that cosmology for this mirror wall is different. The mirror particles also was created by Big Bang, but why we should assume that, okay, they have same numbers, everything, but small fluctuations, any coupling constant will change dramatically their cosmology. And maybe their cosmology is different, and we have some little change in temperature after heating, and then we can avoid the main problem of this, what I say, this nucleosynthesis. So, it is known not only in physics but everywhere, and so, as I told, it was very natural explanation of dark matter. You don't need to introduce any other particles, just say that I have mirror wall, then you can explain all dark matter. Okay, I finished mirror part. Any question? I go now to gravitational waves. I will come back, but okay.
Sure. Very good.
So start about theory. So it is Einstein equation is all this, so but still works, still go, no strikes, no. Yeah. So at first it was claimed by Einstein himself that there is a wave-like solution of Einstein equation in linear approximation. Then they found the problem with the energy of gravitational interaction and claimed that, okay, it's not possible, so gravitational wave probably not exists. So it's a long story about this paper and how it was found and so on. Then Rosen, okay, shows that I have not a tensor of energy, but pseudo tensor, so by changing of coordinate I can vanish energy of gravitational wave, so it means that they don't exist. But real, it was in 50s already, and now new people come, the joke, so it's the quadrilateral dynamics, Landau, Feynman, and so on. So real breakthrough in this gravitational wave experiments or trying of detection was Feynman's words that he said, I don't care what these gravity people say, they are solving some old equations which is not quantum at all. I have some BD stick idea that I have BD stick within space. If gravitational wave goes through, it make waves, and I have friction, and it means the energy. So how we calculate, I don't know, but gravitational wave should carry energy. Okay, it was starting point to detection effort. First was this famous experiment by Weber. Look, he was trying to detect gravitational wave by this cylinder. It was, of course, very noisy, very small. We know now that it was impossible to find waves, because even he claims that he got one signal, but nobody knows what it is, that vibration. Then next step is that another Russian in 1963, they suggested to use Michelson-Morley interferometers, but it should be very large and nobody can build at that time, especially in Russia. And next important date is indirect detection of gravitational wave, and Nobel Prize on this first time. It is a binary pulsar, so they observing how this pulsar losing energy, and then compare with the Einstein formula. It was exact match, so it means that this system losing energy by gravitational waves. So it was, of course, indirect observation. And real observation, it was announced in February, but detected was in September 2015. Okay, it's recent Nobel Prize in gravitational waves in 2017. And I want to mention future missions in space. I want to send this kind of interferometer in space. It's called LIGO. So time by time they change the date. Now they say 2037, but then it can be forever. I don't know.
Right.
It's a very expensive project. Also something is in Japan. They also saying something about the Bessigo experiment. So it's unknown. So in future maybe we have interferometers like LIGO in space. With a huge triangle with larger interferometer and so on. Okay, what might have gravitational waves? It is okay. Chip-like signals coming from binaries, which LIGO which observe now. We cannot observe bars still because if we see bars, you cannot be sure that it is gravitational wave. It can be anything. But if periodic signals, you can somehow notice or extract periodic signal from your noise. Somebody say that maybe we can detect gravitational waves in CMB. We need find so-called B modes, the rotor mode in the CMB radiation. When Planck experiment was finished, 2012, everybody expected next year, 10 years ago, we should have this CMB anisotropy map, but still waiting. I don't know. Maybe no signals or something wrong with this data extractor. And these pulsars. About this is binary pulsars, and you can observe by electromagnetic radiation signals and then detect indirectly gravitational waves. Now about LIGO. So it is a map of existing laboratories. Operating is yellow, and one is planet is LIGO India. They want to build large interferometer in India. Something maybe appeared in China, but we don't know. That's not a running project, but just planning. So we have two LIGO observatories in Livingstone and Hanford. Its separation is 3,000 kilometers. It is real pictures in Livingstone and Hanford, so it's 4 kilometers arms, underground tunnels, where we have laser rays. So it's very difficult to find a mirror on 4 kilometers and take back the signal, but okay, somehow, I don't know details of this experiment. And another similar is in Italy, VIRGO, and it's supposed that this also works. They are part of collaboration, but I think it's not never works, so it just they are part of collaboration and they have speakers, but really they don't work. This equipment, so
Does it work?
yeah, they don't observe anything. So,
Well, you learn something from that too. It doesn't work, right?
so really, we have two American observatories, and okay, we call also we have VIRGO, but fortunately we have now GAGRA, The Japanese just last year it was start operated, and in future we have possibility to make triangulation. What it means? How now we know if you observe a gravitational wave, how we know direction? In VIRGO signals you have time, and by time delay, you assume that the speed of gravitational waves is c, like light speed, and then you can say by time delay the line in the sky from where it comes. If there is a ring, then I have triangulation, and then I can point in the space. But as I told, unfortunately, VIRGO almost not works. So if Kagra will make this third point, then we will be able to point exactly in the sky, because we have Nobel Prize in detection of gravitational waves. We have another signal, but we are not sure that these two sources was the same. So in future, maybe we can check this. So it is Nobel Prize, as I told, it is to their papers. During first round, they observed 3 signals. One was restricted, so it was not real signals, and so we had 2 gravitational waves. And one of them then have counterpart, electromagnetic counterpart, to be sure that it is real effect, not spurious. So present situation now. So we have some effort to find waves, and especially some electromagnetic or neutron signals which coincide with this gravitational, possible gravitational signals. We know that somehow you have a lot of black holes, stellar mass black holes around us. We don't expect. If VIRGO data is correct, so we have a huge amount of black holes in the universe, which is just naked black holes without any accretion pattern. We're not expecting this. So as I told, we waiting for Planck result with anisotropic map to detect stochastic waves in the yearly universe. It is LISA, also I mentioned this. And this Kagra, which starting in November 2021, during third run. And the next fourth observational run for LIGO is scheduled for March of next year. So, and it is planning that third generation of detectors in the European Union and the United States, and also I mentioned LISA, which is should be like quantum detection in very short gravitational waves. So now present situation with LIGO detection. We have now 90 signals which is approved. So we have 3 observational runs. The third run was interrupted because of COVID. Even gravitational waves don't like COVID. And we have 90 signals. From there, black hole coalescence is 84. Most of them are black hole merging. We have 2 signals, neutron star and neutron star. 2 signals with black hole and neutron star. And 2 signals, black hole and unknown object. We don't know what it is. This can be black hole, neutron star, or something else. So it is after third observational run, we have this signal. So only one neutron star merger had an accompanying electromagnetic counterpart in gamma rays, and it was enough to give Nobel Prize. Otherwise, it was impossible, and it is problematic, I already told, but hope that it is correct and we can approve the signals for future observation. So now it is masses in stellar crater. There's some famous computer play. Are you guys playing this game? No? So its name coming from computer play. It is stellar crater. Yeah.
Oh, okay.
Okay. So here you see the mass, and in the X is just nothing. It's presented symmetrically to be nicer. Otherwise, it's very difficult to see. So what it is, we have it is in mass of one object, second object, and the resulting black holes. This red one is black holes which we ordinarily observe by accretion of mass. So it is in the galaxies or somewhere. It is electromagnetic neutron stars, and this blue is what we observe with LIGO and Gogberashvili. It is black holes, and these are LIGO neutron stars. You understand what it is?
Yeah, because you kind of spread it out, because otherwise
Yes,
it'd be all over.
otherwise
right?
you cannot
Yeah,
see it.
otherwise it'd all be lined
Yeah,
up
so
like that.
X,
Now, when you
not
say
many
solar
things.
masses, do you mean of the black holes that are colliding, or what do you mean?
Yes, there are
Okay.
two black holes, one here,
Okay.
8
Two
solar
solar
mass,
mass,
12 solar mass, and at the end we have 20 solar mass black hole. So now have some strange signals here. It is green one is neutron stars. This yellow one is black hole neutron stars here, and this red are black holes in lower mass gap. I will explain what it means. And here is the black holes with upper intermediate black holes, so upper mass gap. So we don't expect to have such a signal, and I will explain all this what it means. So let's start with unexpected events. First, star upper mass gap, intermediate black hole. So there are some models. They say that should be mass gap between 65 and 165 solar mass black holes. We have not such a, we should not have such a black holes, because we have some models to creation of black holes, and if black hole is small, it's a so if it is large, it's direct collapse to black holes ordinarily. If it's in this diapason, gravitational field go to mass creation, positron electrification, and this object blow up without leaving a black hole. And also pulsation of power instability, then part of black hole will disappear, but black hole, their envelope mass will disappear, and in the middle we have small black hole. But at the end, we will have mass gap in this diapason, and before LIGO signals, it was approved that yes, we have this mass gap. We have only small black holes and supermass, and not in this mass gap. So first, what we see that there are several events like these two, which is in mass gap. So to explain this, you need some hierarchical merging. So we have smaller first generation of black hole, they are merging and creating this medium-sized black holes. So there are some models. It is experimental observation of merging rate. So what does it mean? It means 0.002 in gigaparsec volume per year. So less than one event. So 100th of event, one in the volume of gigaparsec cube per year. We can estimate this, and if you say that we have three black holes, which possibility amount of them as 50% very survived for a long time, and merger rate is 20%, then we can obtain theoretically this rate, but it is very extremal assumption to obtain middle mass black hole. We need very extremal assumption about this hierarchical merging. So it is one kind of why we don't expect to have such a black hole. Then another, it is this signal which is most massive black hole. It is so this we have 1 and 2, and in total around 7.4 solar mass system, and then we have resulting object in this mass gap. So we don't expect to have such a massive neutron star. You see neutron stars here, and there is a X binary restriction. We have model, so maximum should be lower gap for this, and so this signal has so it is lower than for black mass for black hole, but very high mass for neutron star. So we cannot understand how this heavy neutron star exists. Then this signal, we have a system where we have black hole and two signals with unknown particles. We have with the mass of this can be massive neutron star or little black hole. It's called with a small mass black hole, also with mass gap. It's also unclear. So these objects are heavier than known pulsars, which we observe electromagnetic radiation, but lighter than any known black hole. We also observe by calculation mass and electromagnetic radiation. Now a little mechanism how astrophysics is working with this. First idea was probably we have primordial black holes and they have a chance to grow and then be in this mass gap, lower and high mass gap, but it's constrained by CMB and micro lensing. We see that there's no primordial black holes on CMB picture. We don't see black holes. Then astrophysical binary system, there are three mechanisms of creation of this, and so all this mechanisms say that theoretically, if you calculate amount of binary black holes, it should be 5 to 10 in gigaparsec volume per year, merging of black holes. But LIGO observed that it is 10 times more. So it is experimental LIGO result, and it is theoretical from what we know from cell. Now, how we calculate merging rate? It is merging rate. Important here is the number of black holes. We can estimate number of black holes. It is formula for number, and important here is the star formation rate. So, and it is formula for star formation rate. It's a half, so semi-experimental formula. Z is distance, redshift, and it is in megaparsec per year, and it is function which have maximum at z equal to 2, and it means look back time in our universe, it is 10 giga-year. So,
when you say number of black holes, is that per volume or what? I mean,
of course, number of black holes that depends on mass, number of stars, massive stars. Number of massive stars depend how they create. Then they should have time to become black hole and then to create binary system. And then you can calculate how many binary systems can be in gigaparsec volume. And it is formula, okay, so it's, I will not go into details of these formulas. So problems now with this observation. So merger rate, which is observed by LIGO, is much higher than we have theoretical predictions. Our calculation gives much less. Then only one, its main problem, only one from 90 event has electromagnetic counterpart. But we expected that any binary neutron stars, mergers should have gamma ray blast, neutrinos or something. Also, when you have black hole neutron stars, also should be some electromagnetic radiation from neutron star. And any black hole usually surrounded by ordinary matter, and their accretion also probably need to emit electromagnetic radiation, but we don't observe anything. Then we observe also mass gap events we cannot explain. So this is main three problems of LIGO observation. So now suggestion that all this can be explained if we say that this detecting signals coming not from ordinary black holes, but this mirror matter which is everywhere. They are more cold and they have a lot of black holes, but we don't see high radiation. Okay, so in mirror world, what we have, it is along ordinary world, was created by Big Bang also, but with lower temperature. It means that from Big Bang nucleosynthesis we constrain that ratio of temperature of mirror world and our world is almost half. So 2 times less temperature at the beginning. Yes? Then from leptogenesis mechanism we see that baryon asymmetry is 10 times. It means that they have 10 times more baryons than in our universe. Abundance of baryons there is much more. Then we can explain all dark matter. This dark matter density or baryon density mirror world in our world, factor 5. And almost all stars are helium stars. Here we have 25% in the universe helium and other 75% is hydrogen. And opposite in mirror world it is 75-80% helium. So mostly their stars are helium stars. It means they are more massive, evolve faster, and so this is example of how faster they can evolve. So they already finished creation of galaxies. If our galaxy is spiral, there is mostly spherical galaxies, and their galaxies are aligned with our galaxies, and we observe them like dark matter. It is spherical. Hello for us, but really we are inside of mirror galaxy, and we are dark matter for them, and they are dark matter for us, because we don't interact with each other, only by gravity. Okay, so what's happened if we have these properties that initial mass function which I use in my calculation is higher in mirror world. Star formation rate peaks at much earlier. We have Z equal to 2 and there Z equal to 10. Look back time almost 13 giga a year. The star formation rate is also higher there. And number of stars is 5 times more than in our universe. And number of black holes, we can calculate 10 times more. What we needed to explain LIGO. Yes? We needed factor 10 for black holes. Okay, so it is last part of our suggestion that merging rate with our amplification of in mirror, it is 10 times of we have theoretical estimation in our work. So its energy rate appears within LIGO observations. Then we can explain easy this hierarchical mergers because we have much more stars there, and without any some strange assumption, we can explain this mass gap objects. And also lower mass gap can be explained much easier because we have more helium stars, and helium stars are more heavy and can be lower mass gap. Okay, this conclusion. So we suggest that in our universe there exists mirror matter in the form of cold dark matter, which we observe only by gravity. In this scenario, the number of the binary system of black holes and neutron stars are much higher, by factor 10. Merger rate is also high and is better explained in LIGO estimation. mass gap object can be explained, and the most important that electromagnetic radiation is natural to explain why I don't observe, because they are mirror photons. We don't see mirror photons. We see only gravitational waves. So it's a main idea that we don't observe mirror photons. They do not interact with ordinary matter. And this prediction, since we have 10 times more black holes there, and also neutron stars, only one from 10 neutron star merger will have counterpart. It will be in our world. Other 9 will be in mirror world. So it is prediction for next running 04 run observation run. Now we have just 2 neutron binary neutron star mergers. If you have around 10, then it will be clear. Observing something or not. If you said just one, means that this idea can be some physical and realistic. So this our publications, it's papers where this result was published. Okay, and thank you.
Great, so we have time for questions.
So, I mean, it's cool. It seems like an interesting way to explain a couple of things going on. And from what I understand from what you said, the main way, I don't know if it's the correct word, but to make it empirical would be if you, in the next run of LIGO, we still aren't seeing an EM counterpart to it, then that's justification for this mirror world, because then we should be expecting.
We again expect no counterpart. We don't see any normal particles except of waves.
So
if it's a lot of signals without any other observation, it is something wrong. Or experiment is wrong, or we have mirror world.
So I guess if that turns out to be not the case, and then we are seeing evidence of it being in our world, what other experiments?
I already mentioned in particle physics, there are several experiments. In particle physics, in astrophysics, we can use mirror model and explain this.
Is there another big one in the works besides LIGO? Or you guys
No, not gravitational waves. I mean particle physics experiments,
Okay.
like neutrino, neutron.
Are the neutrinos kind of a big thing going on right now?
Yes,
That
because
is,
I have sterile neutrino. Naturally, I don't need to extend standard model special. It's just automatically extended because I have not only neutrino, all particles, they are super partners in mirror world.
And it really helps explain why we don't have much antimatter.
Okay.
Is this compatible with the time coordinate for the spinning and non-spinning black holes?
Spinning or not spinning?
Yeah.
There are now some problems that we don't see allies. It means this, yes? We have some observation problems with spin of images. Or I don't understand the question.
Well, time coordinate set up some equation. One set for spinning black holes and one set for non-spinning black holes.
Okay, I don't understand. Spinning back, yes, spinning it means Kerr solution. There is a Schwarzschild solution.
They call time coordinate equation.
Yes, but the Schwarzschild solution is not realistic. Or realistic solution is Kerr. And it should be spinning backward. But there is a problem with how to observe the spinning in images. We have now 2 black holes, supermassive black holes images, and we cannot extract spin from the observation. And it is problem. Some people are working on this, how they align, where is the direction, and how to work. It's another
I think
problem.
that's what I was going to ask about. So when we just have one LIGO operating, right? How much can they tell about the direction of that wave comes through?
As I told, if only 2 detectors working, we have line in the sky because we have only time delay.
Right?
We should measure exactly time, GPS, so
Right.
very small because
If you're saying if two of them are operating, we
yeah,
remember,
and
right?
with some delay you can understand from where it goes.
Right.
First, it was detected by first and by second, or so it's line,
Exactly.
and you said somewhere in this line.
Exactly.
If you have three, then you can save points.
Now, how much is that gonna help everything? When we get three, we can actually tell, hey, right from there.
Yes, because
That's gonna be
we
pretty big,
waiting
right?
for counterpart. We then need to
Right.
look there by gamma ray observatories or by X-rays or something on neutrinos.
Even right at
Yes.
it, yeah, exactly, that's what I'm thinking, that'd be great.
It should observe something. Even the South Pole Observatory neutrino also have directions. And supernova was detected by Neutrino Observatory in 1987 in all direction.
That's huge, that'd be great.
Yes, hi. I noticed that you had in your discussion in the mirror world there'd be a greater helium abundance and a greater abundance of helium-rich 10 mass or higher stars. And I'm wondering, is that prediction or have these observations been made to back up the existence of these helium-rich stars? In other words, is this an observed thing or theorized thing?
We cannot observe anything in your world. Only we can observe structures in dark matter. So it means that if it dark matter is galaxy and it is made with stars, so dark matter has some structure.
Okay.
And if it's mirror matter, yes. And then there is some problems with small galaxies, large galaxies. There are galaxies without dark matter, with melting. So it's another problem. So we can check this model by observation, bigger observation of dark matter and their structure, its structure.
Okay.
I love that you're gonna explain dark matter, that's great.
So it's there's no other model which naturally explain why dark matter is almost the same, not 100 times more or 1,000 times more. So,
I know,
but this automatically explains. It should be within 10 maximum.
You think the James Webb telescope, the observations that we're seeing now, that's bound to help stuff too, right? I mean,
Yes,
shows
James Webb will
crazy black holes and stuff.
micro lensing.
Yeah, exactly, you know, I mean, all of exactly, so I'm sure that's gonna help a lot. And you know, that's why I have hope, guys, when we see those telescopes way out in the future. That James Webb took how many years, guys? Like 25 years? But it's incredibly successful, I think, and so, you know, hey, just gotta hang in there, man. For you young people, you'll see it.
Would that also be like a possible explanation for antimatter asymmetry, like where the intended is more biased for matter and then...
Not really, I don't know. So there's no model, baryon asymmetry. You have baryon asymmetry in mirror and our world, but how to explain baryon asymmetry here? By mirror particles, I don't know. So it's some extra assumption.
So are there any other questions, comments? So if not, let's thank Dr. Gogberashvili. If you want to come down and talk to him more, feel free, and thanks, Pei Chun, for...
Yeah, really, it seems to be.
Yeah.